Have you ever tried to make a seating chart where certain friends just can't sit next to each other? Or maybe color in a map where no two bordering countries share the same color? Well, if you have, you've actually stumbled into the world of graph coloring. It's this amazing puzzle that looks so simple on the surface, but it hides some of the deepest, toughest challenges in all of computer science. So let's dive in and explore the easy wins, the really hard parts, and how we actually solve these things in the real world.
At its core, graph coloring is all about this one simple question. Think about any network, a social network, a map, whatever. If two things are connected, they can't have the same label, or in our case, the same color. So the puzzle becomes, how can you pull this off using the absolute minimum number of colors possible?
Now, in computer science, we have a fancy name for this, of course. It's called a proper vertex coloring. But don't let the name intimidate you. It's literally just one rule. If 2 points, or vertices, are connected by a line, they cannot, under any circumstances, have the same color. That's it. But that one single rule is the engine for this entire problem, and as you're about to see, it leads to some wildly complex situations.
Right, so this isn't just some abstract math problem. It's a super powerful way to think about solving real-world puzzles. Everything from that classic map problem to the logistics of today's massive networks. Let's make this a bit more concrete.
Okay, think about the absolute nightmare of scheduling final exams at a university. We can model this as a graph. Every single course is a dot, a vertex, and if even one student is taking 2 different courses, we draw a line connecting those 2 dots. So what are the colors? The colors are the exam time slots. The goal is to color the whole graph, schedule every single exam, using the fewest time slots, without any student having a conflict. And boom, just like that, our abstract coloring puzzle is now a very real, very stressful logistics problem.
All right, now that we get the idea, let's start with the easy case. Because, believe it or not, some of these puzzles are incredibly simple. You can solve them with just 2 colors. This is kind of the low-hanging fruit of the graph coloring world.
We call a graph like this a bipartite graph. The key idea here is that you can split all the points into 2 teams. Let's say Team A and Team B. In a true bipartite graph, every single connection goes from a player on Team A to a player on Team B. There's no infighting, no connections between members of the same team. And because of that clean separation, you can just color all of Team A blue, all of Team B red, and you're done. It's perfectly two-colorable.
So the big question is, how do you know if a graph is bipartite? Well, it turns out there's this really elegant rule. A graph is bipartite if and only if it has no cycles of an odd length. For example, a triangle. That's a 3-node cycle. You can't 2-color a triangle. Try it, red, blue. Then what? The third point touches both, so you're stuck. But a square, a 4-node cycle? No problem. Red, blue, it works perfectly. This no odd cycles thing is the magic key.
And testing for this is surprisingly easy. You just start anywhere, pick a vertex, color it blue, then find all of its neighbors and color them red, then find all of their neighbors and color them blue. You just keep spreading out like that. If you ever find yourself in a situation where you need to color a vertex red, but it's already connected to another red one, alarm bells go off. You found an odd cycle. But if you can color the entire graph this way with no conflicts, you're golden. It's bipartite.
And the best part? Get this. This whole process is ridiculously fast. The fancy computer science term is OV plus E, which basically just means the time it takes is directly proportional to how many vertices and edges you have. In plain English, it's lightning quick. You can check even a massive graph for this property in no time at all.
Okay, so that was the easy part. Fun, right? But what happens when a graph isn't bipartite? What if you've got a triangle in there, and you know you need at least 3 colors? Well, this is where we say goodbye to the comfortable world of fast, simple answers, and we walk straight into a truly, truly difficult problem.
The question we're asking is fundamentally different now. We're not just asking, can we do it with 2 colors? We're asking, what is the absolute rock-bottom minimum number of colors required to color this graph? And that number has a special name, the chromatic number. Finding it is one of the most famous problems in this field, because that tiny change in the question makes all the difference.
I mean, just look at the comparison here. The bipartite check is a simple yes or no question, and we get the answer fast. But finding the chromatic number, that's a quest for the perfect optimal answer. We've gone from a sprint to an absolute marathon. It's the difference between asking, is this door unlocked, and what's the secret combination to the safe inside?
And that brings us to this big, scary term you might have heard of, NP-hard. Finding the chromatic number is an NP-hard problem. What that means is there's no known algorithm that can solve it efficiently for every graph you throw at it.
As the graph gets bigger, the time it takes to find the perfect answer explodes. We're talking about the kind of problem that could take the fastest computer on Earth longer than the age of the universe to solve for a big enough graph.
So, if finding the perfect answer is basically impossible for large graphs, do we just give up? Of course not. We're engineers. We get clever. Instead of looking for one single magic algorithm, we use a whole toolbox of different strategies to attack the problem from all sides. So here's the game plan in the real world. First, you box the problem in. You find a lower and an upper limit for the answer. You know it has to be somewhere in that range. For small graphs, you can actually use a kind of smart, brute force method called backtracking to find the exact answer. But for the really big, gnarly graphs, we use heuristics, which are basically just clever rules of thumb that get us a pretty good answer fast.
Let's break those bounds down real quick. The lower bound is just the size of the biggest clique in your graph, a group of nodes that are all connected to each other. I mean, if you have a triangle, you know you need at least 3 colors, right? That's your floor. The upper bound is even easier. You just find the one node with the most connections, and the answer will be, at most, that number plus 1. The real answer is somewhere in between.
Okay, let's see this backtracking thing in action on a simple triangle. Let's pretend our computer is trying to solve this and it doesn't already know the answer is 3. How does it figure it out? Step 1, it grabs a vertex, any vertex, and just gives it the first color available. Let's call it color A. So far, so good?
Next up, it moves to a neighbor, vertex 2. Now it knows vertex 2 is connected to vertex 1, so it can't be color A, no problem. It just pulls out the next color in its palette, color B, and uses that. Still no conflicts.
But now we get to the tricky part. Vertex 3. It checks its neighbors. Uh-oh. It's connected to vertex 1, which is color A. And it's also connected to vertex 2, which is color B. So, what color can it be? It can't be A. It can't be B. We're totally stuck.
And this is the moment of truth. The algorithm hits a wall, a conflict. It realizes that with the colors it has available, just A and B, there is no possible solution. It's forced to recognize that its current path is a dead end.
So it has to backtrack. And in this case, that means opening up a new can of paint. It introduces a brand new color, color C. And voila, vertex 3 gets color C, the conflict is resolved, and the graph is colored. The algorithm has found a solution. And in the process, it proved that the chromatic number is 3. That's the core idea. Try something, and if you get stuck, go back and try something else. Okay, so we've journeyed from the easy stuff all the way to the ridiculously hard problems. You might be thinking, this is a cool puzzle, but why should I care? Well, it turns out this isn't just theory. Graph coloring is a model for solving an incredible number of real-world problems.
We've already talked about scheduling exams, but that's just scratching the surface. This is used inside the compilers that turn your code into runnable programs. It's used to assign frequencies to cell phone towers so that don't interfere with each other. Even solving a Sudoku puzzle. Yep, at its heart, that's a graph coloring problem. Anytime you have a set of things with constraints, where this can't be next to that, you're probably looking at graph coloring.
All right, let's boil this all down. If you're heading into a technical interview, this is your cheat sheet. When you hear about checking for 2 colors, you should think bipartite. The key idea is no odd cycles, the algorithm is fast, and the answer is a decisive yes or no. When you hear about finding the minimum colors, you should think chromatic number. The key idea is optimization, the algorithms are slow and complex, and it's NP hard. It's all about that distinction between is it possible and what's the best.
And that just leaves us with a final thought. We started with what seems like a simple problem from a kid's coloring book. And by digging into it, we ended up at the very edge of what is computationally possible. It really makes you wonder, doesn't it? What other simple-sounding problems are out there just waiting to reveal some mind-bending, impossible depths?